Thank you for coming today. I'm going to talk a little bit about causal assessment. We'll be hearing a few more talks about this topic. And some of you are already familiar with some of the causal assessments that we've done in California as part of the bioobjectives development process. And you heard from John earlier today that it can be a rather intensive and somewhat of a cumbersome process. It's, however, really important. If you've read the recent PSA management memo, you would realize that we have quite a few streams in degraded condition in California, and causal assessment is essential if you ever want to do anything to fix them. But, you know, it doesn't have to be that hard. There are a lot of benefits we have in California, and what I'm going to talk about today are some of the ways we can sort of harvest those benefits. And there's actually two things that I'm really focused on today. One is that we have the California Stream Condition Index, and two is that we have a number of large-scale biomonitoring programs that have developed fairly robust public data sets. So you can put the two together and make causal assessment quite a bit easier. So our vision for causal assessment, we've been talking a lot about this at SWRCB and with a lot of our partners, and we see that we probably need to have two tracks on doing causal assessments. We want to have, first of all, well, the second one on this list is a sort of intensive causal assessments, and you'll actually be hearing an example of that next from Jerry Diamond. And that's where you go through the EPA's CADIS-like method. CADIS is Causal Assessment Diagnostic something or other. It doesn't actually have to do with any bugs, but it's a fairly intensive process of analyzing data to strengthen or weaken support for different types of stressors. But we think we need a simpler method that you can use on a large scale, on a routine basis, something that you could do at dozens of sites in a matter of hours at most. So something that you can really just use easily. This would give you a good idea of what kind of work you might want to do next. And you'd basically be doing this at almost any site that gets a low score. More intensive approach you would basically reserve for more strategically selected sites. So to do causal assessment, you have to have comparator sites. Comparator sites, this is probably one of the biggest challenges in doing a causal assessment. But what they do is they provide you evidence of what a stream might look like if it was under a different stress, or saying different levels of disturbance, and that can let you figure out if that disturbance is really responsible for those low scores you're observing. We've identified about 3 criteria that we think is valuable in a comparator site data set. You want your comparator sites to support similar biological condition, that is, if they were in unstressed circumstances. The comparator sites should represent a range of biological condition, and preferably you include sites in your comparator data set that meet your desired objective. For example, it's in reference condition if that's your objective. And 3, you want to know that your comparator sites represent a range of different stress levels. The California Stream Condition Index actually directly addresses 2 of those 3 criteria. You've heard a lot about the CSCI. It's a predictive index. It basically looks at the environmental setting of your stream, looks at the basin characteristics, and it predicts what kind of taxa you might find at your site and what your biological metrics might look like. And you measure condition as a deviation between your observed and expected biological condition. So that means you're getting at least 2 of these 3 criteria. 1, it can tell you if your 2 sites could support similar biology, and 2, it shows you the range of conditions that your data set has. It won't tell you anything about stress levels. You really need to bring in non-biological data to look at that. So we haven't really gotten all the way there, but the CSCI really does help us get at least those first 2 criteria. This is just a really crude example of how comparator sites are used in causal assessment. I think you'll probably get a better example of this in the next talk. But basically, you're comparing the biological condition at your test site versus your comparators and seeing if increasing a certain stressor is associated with a decline in biological condition. Don't look too close, but basically what you're seeing in this example is that stressor A, there's not really good support in this data set, but there is better support for stressor B. So how do you pick comparator sites? There's the traditional method that is recommended in some of the original EPA CADIS documents. Typically, this is done through best professional judgment or BPJ type exercises. You're often looking at sites upstream or downstream of your test site. And there, basically, you have local experts decide what sites they think are going to be best suited to the analyses you want to do. Typically, these are oriented around point source problems. It's a lot easier to see impacted and unimpacted sites. And generally, they're assuming that you don't have a ton of data available to you. You don't really have access to any information of what's going on outside your watershed. And you're typically selecting your comparators based on how close they are to your test site, and you're assuming that there's some kind of environmental similarity. This is an example of our case study in the Santa Clara River that we used in the bioobjectives process. The red site was our case site, and then all these sites up and downstream were used as comparators. But California is a different situation. We have huge data sets at our disposal. This is thanks to the PSA, the Southern California stream survey done by the SMC. We have our reference program, and the Bay Area has their own reference program, probabilistic program that also could provide a lot of data to make causal assessments a lot more effective there. So you almost have the opposite problem. You have thousands of sites you could choose from. How do you know which ones are the best to go with? So the CSCI offers one way to do this. Now, the CSCI has a couple different components in it. One of them is this O to E index that Michael just mentioned. Basically, you look at your environmental variables, things like precip, elevation, latitude, and you use statistical models, and you can translate that into capture probabilities at your specific sites. You know which taxa you expect to find and how likely you are to observe them at your test site. If you do this for a bunch of sites, you can take a site by taxon matrix and easily just transform into a site-by-site similarity matrix, or in this case, it's expected similarity. So the CSCI can help you figure out how similar two sites might be if they were both in natural condition. We decided to see if this would be, how this might look if we tested this out using some data from Southern California. We have a large pool of potential comparators driven from various surveys, the SMC, the EMAP program, the PSA. So we had about 700 sites to choose from. We looked at 3 sites that have been used in causal assessment case studies in Southern California. We have the Santa Clara River in LA County, San Diego River in San Diego County, and then the confusingly named San Diego Creek in Orange County. These are actually 2 very different sites. But we also were worried, 3 sites, that's nice, but we want a little bit more of a data set. So we also handpicked 12 low-scoring sites and just added them to the mix. And we then decided to look at how similar they were to all the potential comparators in our larger data set. So to look at this map, basically each of our test sites is shown on this axis here. These are the 3 from the case studies, and these are the 12 that we handpicked. And on this x-axis, I'm showing the expected similarity of all our potential comparators. So we have about 700 points along each of these graphs. The ones on the left represent comparators that are expected to be pretty similar to your test site, and the ones on the right represent those that are fairly dissimilar. And you can see that there's a lot of different patterns you observe at the different sites. So one of the first things we observed is that the best comparators aren't always right next door to your test site. In these plots, I just showed the 10 closest potential comparators. Those are those purple dots. The yellow triangles are the test site. And they tend to come from all over the region, or at least, from, within 100 kilometers. The data set I was looking at was constrained to Southern California. If I did this statewide, I might have ended up picking comparators from other parts of the state. If you look at the patterns in that graph that I showed you earlier, you can see some really interesting patterns. You can see that there were a few streams that it was a lot harder to find comparators than others. And here we have San Diego River on the top and San Diego Creek on the bottom, so San Diego County, Orange County. And San Diego River, we have a lot of comparators that have fairly good similarity to our test site. In contrast, San Diego Creek seems to be a lot more unique relative to the probabilistic data set. It's going to be harder to find similar comparators for San Diego Creek. If you remember, I said you want to have a range of biological conditions in your comparator data set. So what I did is I took all those points and color-coded them in one of 3 categories. The blue dots represent sites that were meeting our management objective. I used the likely intact threshold that Calvin presented to us earlier today. The green sites represents streams that might not meet those objectives, but still had higher scores than we have at our test site. And then the red dots represent those that were actually worse than our test site. And if you look closely, I'll show you a few different patterns and how you can interpret what they might mean. There were a few sites where you just didn't really have a lot of comparators meeting your objectives. So in other words, all those blue dots start fairly far to the right on these plots. These might represent regions, certain types of streams that have been so pervasively altered that you generally don't observe streams to be in similar good condition. These might be the large, low elevation, sandy bottom streams in Southern California. You found a few cases where, among the set that I showed you, here are a few though, where your test site is actually worse than all of its closest peers. And what that tells you that you actually probably could do better, even if you can't quite achieve reference. You have a lot of these green dots occurring to the left side of the plot relative to the red dots. So that means that your closer comparators are all doing better than your test site. You also see the opposite pattern where your test site's in fact doing better than all of its peers. So in this case, you have the most similar sites are all these red dots to the left of all the green dots. We wanted to do a little bit of a head-to-head comparison between this quantitative predictive approach and the traditional BPJ approach. And so you see the top 10 comparators selected by the predictive approach on the left, and on the right you have all the BPJ selected comparators. And you find, there's actually not a lot of overlap between these two. There were a few sites that were selected by both, but generally you're selecting a very different set of sites. You had a lot of geographic constraint among the traditional approach, and that's not too surprising. They generally were just looking in their immediate vicinity, whereas you generally saw comparators picked from all over the region by the predictive approach. I don't want to contrast these two to say that the predictive approach is necessarily better than a traditional approach. I think these are actually, I think what it instead offers is a better starting point for evaluating comparators than just sort of a naive BPJ approach. In that it gives you a bunch of sites to start evaluating it, but you still want to apply your local expertise to know if the sites that these algorithms are recommending to you are the right ones for what you need to do. There are a number of benefits of this approach. First and foremost, they really help people look beyond their watersheds. They help them access these very large databases and see what's in there, what other data are available, even if it's not a site that they're at first familiar with. I think it's actually very valuable that this approach is directly linked to an index that has some management relevance, the CSCI, and that's better than making assumptions about what kind of environmental gradients may or may not be relevant for biological similarity. One of the biggest advantages of this approach over the traditional approach is that it's easy to pick 100 sites this way. A traditional approach, you're at best limited to maybe 6 or 7. And it's hard to get even that many. You just don't get a lot of sites, and therefore you're not really able to do some of the more sophisticated analyses you might want to do in your causal assessment. We also think there's actually a number of other applications of this kind of approach outside of causal assessment that we just think could be really interesting. You could, for example, pre-screen sites that you're going to incorporate into permit-required monitoring by selecting sites that you think should be good comparators. You could also use it to evaluate mitigation sites to see whether or not you're replacing a degraded site with one that should support similar biology. We're right now exploring the trade-offs between having high numbers of sites versus degrees of similarity. I didn't have any cutoffs or criteria of what I think is a maximum distance value. We still don't really have a good sense of what similarity is enough for most of these purposes. But if this approach works and we develop it, we think it'd be easy to develop an interface for some of these public databases like CEDN or the SWAMP databases that could really help people query out all the data they would need to do a causal assessment for a given test site. It would be fairly quick, and then that would actually lead to the easy implementation of some of these coarse causal assessment tools that I mentioned earlier. And with that, I'm actually all done. So, questions for you guys. Sorry.
So you really didn't talk about using some of the traditional water quality data that's also embedded in these sampling programs, and I was wondering what your thoughts on that were.
So I think it would be, okay. So like I mentioned, when you want your comparator site data sets to include sites that represent a range of stress levels, and I think that at that point, that's where those types of measures would come in. So you look at your chemistry data, you could add a query to say, okay, let me at least evaluate whether these comparators have more copper or less copper, higher oxygen levels, lower oxygen levels, because you want to have those factors in your selection process for picking a good data set. So I think that would come next. I kind of was like silent in all the stressor data, mostly because I didn't have time to work that out in this example for today. Yeah, I think that would be the logical next step.
Rafi, great talk as always. Really, really stimulating stuff. I have a couple questions, but I'll just ask you one of them. And it sort of builds off what Terry asked, and that is, have you thought about, at least for the course screening, which I think is really cool, and maybe this is what you have in mind when you said on the last screen you're working on this, is to combine the pattern of stressors with those populations to say, well, this is the biological expectation is similar for these two sites, and they're similar with regards to every stressor except for one. And one of them has good biology and one of them doesn't, or at least for just a couple, to help quickly screen through some of the stressors that might be driving that.
Yeah, that's very much what we're thinking. I think for these course scale tools, it would be a very limited array of stressors that we could include in something like that. You'd want certainly all the ones that we use in our normal PHAB assessments, and probably you could add nutrients to that. Something like metals or like pesticides, it would be a little harder to do that, but ideally you could incorporate that. Ultimately, you'd probably need to take a closer look using the more traditional CADIS approach to sort of verify those results.